So we just discussed the algorithm right here. So let me just go through the example one last time with the algorithm. So we have to start the program and get the list and the target. I've gotten my list right here and I've set my target as 8. Then we have to initialize start as 0, end as n. So start has been initialized at 0 and then the end has been initialized as n being the length of the list, and here it will be 11, but the index value would be 10. So then mid will be -1 and position will be -1. That's for you to define in the code. And then the while loop will be started. So while start is not equal to end, here 0 is not equal to 10, so we can enter the loop. So we'd calculate mid is equal to start plus n divided by 2. So mid is equal to 0 plus 10 by 2. 0 plus 10 by 2 would be 5. So the fifth position, 6, would be the middle value. Then we should calculate if compare if target is equal to list of mid. So the target would be 8. So is 8 is equal to list of mid. So mid will be 5. So list of 5 is 6. So is 6 equal to 8? That is, the target is equal to this. Is that true? No, that is false. And that if that is false, then you go to checking if that is greater than if target is greater than the middle value. So if the target is greater than the middle value, yes, the target is greater than the middle value. So take the right hand side of this. That is, we change start is equal to mid plus 1. So start is 0 right now. So mid is 5. So mid plus 1 would be 6. So start would be now 6, end would be the same 10, and now we enter the loop again. So while entering the loop again, we calculate mid again. So mid is again calculated as start plus n by 2. So start plus n by 2 is 6 plus 10 divided by 2. That is 8 right now. So this is the mid, and you just repeat the process. You compare target and now mid right now. So now mid is 9 and the target is still 8. So 8 is equal to 9. No. Then you check if it is greater than 8 is not greater than 9. So then you check if it's not greater than 9, then you just change the end is equal to mid minus 1. So the end is equal to 10 right now, so it will be changed to mid minus 1. So 8 minus 1 will be 7. So the start is 6, the same thing, and end will be 7 right now. So basically the same thing. Since they are not equal yet, you go through this one more time, and you calculate mid another time. And once you calculated mid, you would compare it again. They are not equal, so 8 is actually greater than 7. So again, if grade 8 the target is greater than, then you add start is equal to mid plus 1. So mid right here is actually this position right here. So 6 plus 1 would be start would be 7. So start and end are now equal. In that case, if start and end are equal, now you see if start and end are equal, then you check target is equal to list of start. So list of start, list of 7 would be 8, and the target would also be 8. So since they are equal, the position would be this value right here. Position would be equal to start right here, as I've written, and position would be equal to 7, and that would be printed as the output. So this is the binary search. And this is just how the code might look like of the algorithm right here. So you would have an array as an input. I just defined the array right here. You would typically get the input from the user. I've given target. You would get it from the user. Then you initialize start as 0, and I know the length right here, so I've just given it as 8. Position and mid are set to -1. Then the condition while start is not equal to end. Then you would use the mid value. You'd calculate the mid value as start plus n by 2. Then if target is equal to array of mid, that is the array right here of mid, and then you just do that calculation. If that is equal, then position is equal to mid, and you break the loop right here. Else you'd check if it is greater than or less than, and accordingly do the calculations right here, and that loop will go on until start is equal to end. So when start is equal to end, you just have the if target is equal to list of start, and then position of start, position is equal to start if that is true, and then element is found at that index. If this is not true, then element is not found in the entire list, and that is the code. Now let's look at its complexities. So time complexity right here. So for binary search, the time complexity would be big O of log n to the base 2. So this is because each comparison that you do in that list, it leads to then the list getting halved. So that means like the half the number of comparisons that you might have to do. So example, if you have like 2040 elements in a list, one comparison would lead it to basically half the list. So that would be 1024 elements. That comparison of the middle value would give us 512 elements, and it will every time it will just get halved as you go. So that is why we have a logarithm to the base 2 right here. So that is the time complexity of binary search. The space complexity is big O of 1. This is because there's no new lists needed, no new linked lists or arrays needed to be created. It's just three int values, start, end, and mid. So int values, space taken by int data types are very minimal. So the space complexity is big O of 1. Then the advantages and the disadvantages. The advantages of binary search. First, you have it eliminates half the list each comparison. This just leads to a better time complexity, as we saw right there, if you compare it with linear search. Then it indicates if the target would be before or after a compared element. So once you compare the target value with the middle element, the current middle element, you would get to know if the target is after the middle element or before the middle element. So that is an advantage. So it works significantly better than linear search in larger lists. So last time when we were looking at linear lists, a linear search, I asked you guys to imagine 1,000 element list and how you'd have to like search every single element, like 1,000 comparison you have to do to search the particular element. Binary search doesn't need 1,000 times. You could just half it each time. So with one comparison, it will go down to 500. So 500 will go down to 250 in two comparisons, so that will be 125 in three comparisons. So basically you'll go through the whole thing in like at the maximum 10 comparisons in binary search. However, in linear search is the same 1,000, just have to go through that 1,000. So that is why it works significantly better in larger lists of linear search. And the disadvantages is programming this tends to be error prone and difficult. It might be tricky to change like depending on the target being greater than the middle value or not, you would have to change start or you would have to change end. So that might be an area while people might make mistakes when you're programming that. So that's a disadvantage right there. Then then it needs the list to be sorted, which may add up to the time and space complexity. So depending on what sorting algorithm you use to sort the list, it will take, like if you need bubble sort, as I said, like if I imagine 1,000 elements, then if you use bubble sort to sort the 1,000 elements, it's not that of a good sorting algorithm. So that will take its own space complexity, its own time complexity, thus rendering binary search kind of like in the worst side. Linear search is definitely far worse than that, but like it adds up to the time and space complexity. So that's one thing to consider. Also, another disadvantage I'd like to point out is like if you're using very small lists, like with just 5 elements, as we saw in the linear search example, you're better off using linear search, because binary search would have to like search, it'll have to calculate the middle value, then you'll have to compare it, the target element like 2 times to figure out if it's less, the target is less than that middle value or greater than it, and then it will have to calculate another middle value. So instead of that, you can just do 5 iterations, and just luckily, if you're lucky, the target value might be like in the second position. So in linear search, you would just get the result in two comparisons itself. But just as it's increasing the number of as the length of the list increases, binary search becomes more useful and far more superior than linear search. So the last thing would be seeing is just a little comparison between linear and binary search. So if you guys understood linear search and binary search, then you guys would be able to write this on your own. So I'm just giving like key points, like what would be the key comparisons. So linear search, it searches the target element in a sequential manner, so like one element by another, it will search and get the target. Binary search, however, it goes like it calculates the middle value and then eliminates half the list after each iteration. and then you guys would be writing about time and space complexity, how time complexity is big O of n here, and time complexity here is in the binary is big O of log n to the base 2, but space complexity in both cases is big O to the big O of 1. So in linear search, you don't need a sorted list to work with. However, in binary, you do need a sorted list to work with. And then linear search, it just requires sequential access to the array or the list. You just need to sequentially access each data element. However, binary search needs the random access of data element, because suppose in a linked list, you would need the random access to just, because half of the list is getting cut out, so you need that random access to move your pointer from place to place to compare your target with that element. So these are just some comparisons between linear search and binary search, and hopefully I've covered everything on these two topics, and I hope you guys understood. I hope I wasn't too fast anywhere. So thank you guys.